Hello viewers, welcome to my channel Science to Technology. In today's show, Rocket Monday, we're gonna talk about Double Asteroid Redirect Test or DART from NASA. So let's dive right into it. Now, what's the idea behind it? Well, idea is realistic, as in at this point in time, as in 2020 or 2021 or 2025, Earth is 100% unprotected, meaning the biggest boom device on this, practical planets, which does not include a star, we have no defense against it, meaning planet destruction class events can happen at any moment in time and we cannot do anything about it. Now you have to understand the context here. There are tsunamis that are very brutal, that cause huge amount of loss of life and property and all that jazz. There are supermassive volcanoes which are really brutal, as in they can literally erode 90% of biodiversity and life form from Earth. But then we have asteroid. Now this is tiny asteroids. There are huge asteroid, which if we are really unlucky, you are talking about a system that is so powerful that can remove Earth from its orbit. I mean, like literally it will change the orbit, meaning you will like, wait a minute, we had 360, it could become like 370. That's how bad that can be. So it is planet ending class event. Now, reality is, as in like we have been observing other planets, meaning Mercury, Mars, Venus, Jupiter, Saturn, Uranus, Neptune. Reality is all of them are getting bombarded. Mostly the big gas giants are kind of acting as our filter because they are getting bombarded the most. But reality is it's gonna happen. It's not a question of if, it's a question of when. It's like when you are born, the only thing that is fixed with you is that you're gonna die. The only question is either you're gonna die in 5 years or 50 years or 500 years. That's the whole point. So same happens here. At this point in time, we are in a shooting gallery and we have no defense system on one of the most brutal thing that space can throw at us. And we really don't want to act like a dinosaur at this point in time. And we have no idea about countermeasure effectiveness, meaning on paper we have 10,000. Oh, we can if an asteroid is coming, we can paint one side. Do we know it will work or not? The idea is like if it's gonna create uneven heating, just enough photon pressure could swing it, and you only have to change the direction by fraction of a degree and it will get the job done. That's awesome, but here's the, do we know how it's gonna work in real life? No. We can have something hitting it. Do we know it's gonna couple the energy properly? We have no idea. Reality is we are blind. We are completely unprepared. We have no idea about anything. So that's the serious reality of it. So target was selected very carefully. Dimorphos, a binary asteroid. Now you may be like, that's a bit odd. Why the heck we are choosing something rare as binary, asteroid? Reality is, if you actually directly target something big like this, and with a tiny thing that we are saying at a slow speed that we are sending, it will change speed and velocity, we think. But here's the, it would be so minute. Detecting it, analyzing it would require equivalent of like having multiple hours constantly observing this puppy. That is flat out not feasible, so to say. So reality is, and this also has the another benefit, it crosses Earth close enough that utilizing radar imaging we can actually observe it. So this is the actual real world radar observation. Utilizing this mathematics, NASA has created this diagram. Everything else you see is just a CG rendering, but this is the reality. This is a binary star system, I'm saying binary asteroid system, which is primary asteroid being Deimos A, 780 meter in terms of diameter. So it's a big boy. And we have satellite Deimos B, which is 160 meter. Now, be mindful, 160 meters still is a significant thing, and this is a complete solid mass. So it's not like oh, we have skyscrapers that are bigger than that. Skyscraper is not dense, this puppy is dense. So this is significant amount of mass. Now change in satellite orbit is easy to observe. The idea is that we're gonna go whack this puppy. Now when we whack this puppy is gonna orbit this. Now that orbit change will be much easier to observe compared to changing observing the velocity of the parent system. It will be much easier. It's like you can just have a stopwatch. Now given the fact that humanity knows how to make amazingly good clocks known as atomic clocks, we can observe minute changes on this puppy. That's why we are selecting binary, and that's why we are selecting this puppy, exactly because we can observe the radar passes very reliably. We can be like, no, we impacted this puppy, this was our prediction, and this is how much data change happened. So this is perfect target, quote unquote. And the orbit right now, this puppy has 12 hour of orbit, and we are expecting to change it, shorten it a bit. And if it was even in few minutes, we can easily observe it. And the target is like 15 minutes negative, so should be easily observable. We impacted energy, how much energy was coupled, how much effect it had, all those should be super easy to calculate in real life. So launcher, now here's the interesting part. This mission, while it does have significance to humanity, it is not a what we classify as tier 1 mission. Tier 1 would be like International Space Station. Unfortunately, James Webb Telescope also reaches tier 1 status, but you get the point. Like those sort of missions, they get GG amounts of money. This does not have that. So, due to low budget scenario, NASA had a realistic expectation. Is like we can only send this puppy with as a second satellite, doing ride sharing to anything that is being sent to geostationary orbit. Now, back in the day, that was the only option, and they designed this mission. It has been working in the background for a few years, so this was expected. The ion engines is not there just for the show. It's also supposed to help boost the orbit. So everything about this puppy was designed like that. It's like, okay, we're gonna go to geostationary, then we're gonna slowly raise the orbit, and we're gonna go our final injection burn. However, when the bidding was actually done, SpaceX is like, bro, that data is outdated. The money that, like, SpaceX is like, okay, everybody is asking you around 100 million, 200 million, or whatever have you. We're gonna do that in 69 million. I don't know. I really hope it's not 69 million. That's really weird. But like, that's the whole point. The bidding was the lowest, and they can give you a complete rocket. Like, dedicated ride. No ride sharing, dedicated. Just go where you need to go. Basically, eat you exactly where you need to go at the speed of 28,000 13 kilometers per second. So at 55 minutes from launch. So, and that's why you can see it's a reuse space stage system, and this also shows how much confidence NASA had built on it, because earlier days they were like very clear, dude, for our mission you cannot use a reused booster, you have to use a clean boosters. But slowly, as with more and more and more and more experiments, they're like, yeah, dude, this is a low priority mission, just go YOLO on it. And even for something like crew rocket system, they are like far more accepting and accommodating of reused booster. So that is really important reason why they can drop the price so low, and that's why it looks like giant fairing teeny tiny satellites. This is a person. So that's the whole point. That's why it's so hilarious. And now you can understand this cost cutting of SpaceX is really starting to have an impact, because till this point, every Tom, Dick, and Harry was like, SpaceX is making it, but it's not actually doing that. Most of the satellites still being launched by Atlas, ULA, or things of that nature. Why? Because satellites are booked years in advance. This is the first time now you can actually see, oh, now any new fresh bidding war that has been done at that point in time, SpaceX is like, bro, don't even come here. Don't waste your time. So that's the reality. At this point in time, SpaceX is actually starting to take people's lunch away. Before this, it was like, they were pre-booked, so they were like, yeah, we are set for like next 4 years. Now it's like, oh, new biddings. Yeah, we really can't actually compete with this sort of price. Flat out can't. So that is also a significant milestone. Now, be mindful, even though this is an important thing, this is designed as a test bed, meaning there's no true scientific instrument, or like, this is the first time we are testing a laser rangeometer for laser system that are being used in Curiosity rover is being tested in asteroids. No, it's a very dumbed down system. It's very simple, as minimalistic as it can be, while being a test bed, meaning try out as many new things as you can. Get the core stuff down. So for example, the core ion engine that has been tested for 5 years, yes, continuously running for 5 years, because ion engine is supposed to work for decades, so they can only test it for 5-6 years. And they had really good experience with this puppy, as in like the erosion of the electrodes are very little. So in principle, this puppy can go work for many years. And if this mission provides real world data and it's positive, I'm pretty sure they can utilize this puppy to do deep space mission, like going to Pluto, going to Jupiter or Saturn much faster. So DART is classified as an impactor, meaning go bam. Now, mass at the launch would be 610 kilograms. It also has thruster and propellant for ion engines, and the huge roll-on solar panel. If you have watched my recent video, this is a very big deal. Now, this puppy is 6.6 kilowatt. To give you a context, that's an Indian household. I'm pretty sure that at 6.6 kilowatt, you can actually power a Western home also. So that's a lot of power. And because of the architectural simplicity of roll-on, it's surprisingly small. So this is a very significant improvement. And you will see this is next gen roll-on. Now you will like, wait a minute, didn't they just installed roll-on on ISS? If they had next gen, why the heck they did not use the next gen into ISS? That's the whole thing. That previous gen, quote unquote, previous cell designs, those have been tested. So NASA was far more accepting of that. This is a go YOLO mission kind of thing. So they are like, okay, let's experiment with it. And in this experiment, you will notice there are flaps like this. Now, idea with that is this flap is much better than having more cells. Cells are far heavier compared to these flaps. So idea is you're gonna have reflectors. Reflectors gonna improve the cell efficiency so much that rather than having more cells, you will have just more reflectors. So that will reduce your launch mass significantly enough. Now, this is a trial at this point. That's why you will not see the whole panel, covered with this reflector. Only a small section is done with that way, and they can observe it, get a comparative data. It's like, does it really translate in deep space? Yes or no? So next roll on is a very big deal. Next engine, yes, the engine is named next, and they also have a small CubeSat, and this puppy is just to there, like once it's actually starting to go yellow on it, it's gonna pop back, and it's like, okay, I'm gonna observe this thing. Now at the point of impact, they are targeting 500 kilogram, meaning they are supposed to expand most of their propellant, and target velocity is around 6.6 kilometer per second. Now that may sound fast from asteroid's point of view. That's like, eh. So that's why it's not as clear. That's why, like, if this was like 60 kilometer per second, at that point, yeah, we're gonna hit the major asteroid, and then yeah, if you're hitting even at half ton 60 kmph, that's fast enough, that's high enough energy event that you will be like damn sure it's gonna change the orbit or orbital path of any body. So right now we are not that fast enough, but we can be. If this engine performs realistically, if something is far enough, then we can in principle actually gain up enough speed where this 6 can become 60, but it will take years. Now what is the hope with this system? Well, reality is real world data. You observed a asteroid. How long did it took you to, okay, we got the how long it took you to find down the, refine and be damn sure with the orbital assessment? Because when you have something, you have to have a rough idea. To get that rough idea to absolutely precise idea, you need to do multiple observations from multiple instrument, multiple time frames. All that, how long did it took you, like that step? All these things are real world things. It's not like a movie. It's like, we have got this, like it takes months to process that. This is the first time NASA is learning all those steps, and doing this, they can optimize it. They were like, okay, this is the protocol, this is how we're gonna do it, and this is a practice run for it. So that's awesome. Another aspect is energy coupling is the biggest issue with this, because this is Dimos, this is Dimorphos, and we're gonna go whack into this. But here's the deal: we do not know what's gonna happen if we hit it. This is one of those things that you may think when you are making a projectile weapon, it's like faster is better. Yes and no. You could reach a point where you literally are penetrating rather than doing damage, and that's why hollow point was created. That's a real thing. So you could even have something similar with that. Like, let's say you are going 670 kmph or even 100 kms. Let's say you run your iron engine as GG amount of power it was running on NASA's kilo power watt reactor, and you're like used to Falcon Heavy at full force. Everything is awesome, but the moment you hit it, it's like you deposited enough energy. Most of the energy turned into photons, as in like flash, and then like a big chunk blown out the other side. The velocity did not change that much. That could happen. We do not know the coupling efficiency. That is why this is very important. This is the original orbit, and we are projecting the orbit change. How much that orbit actually changed? Meaning, what did it happen between here? Did it happen exactly here? We don't know. We flat out don't know. And if you want to know like how exactly we, like how clueless we are, observe all the asteroid return missions. It's like we are like, oh, it did not work. We thought it's much more strong, it did not work. Like, we have no idea. We do not know the coupling efficiency. And observation path and orbit change over time. This is also a critical aspect. If we detect a planet boomer kind of a asteroid, we don't need to move it very far if we detect it far enough. Basically, if we are detecting it, oh, it's gonna hit us in 2 years, we don't need to move something like we're gonna change its direction by like one whole degree. It's like fraction of a degree will do the job. Now those sort of thing, we think our computer says that, our mathematics says that. We have to test it to know for a fact, and like by how much. So this is, all those things are very important. On top of that, all the new data from satellite, basically solar arrays, engines, those will translate to much bigger and better missions for the future. So there are a lot of hope riding on it. Even though this is a low priority kind of mission, it is surprisingly important for the humanity. So this was my presentation on NASA's DART mission. Hopefully you have liked it, learned from it. In that case, please click the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me extra disappointment. Please leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.